Okay, so today I'm going to be talking about a library that I made, which is kind of it's a module that I made, which is inspired by Roact, which I've used extensively for not just creating like UI in Roblox, but also as the sort of main backend of metaboard, and it translates the data that defines the lines that you're drawing on the board to the actual instances that get created. So, like in the actual workspace, it creates these lines. That's surprisingly dark. Is this just a shadowy board? That's a white line.
Yeah, I think the through somehow the sharing process, it's looking darker than it usually does.
No, it looks dark on my screen as well. I'll just open up the thing. Um, yeah, so here we're looking at the frames version, but there's also uh, on the actual uh, physical board itself. I can just walk up to it, I guess. Uh, yeah, it's really dark. I think it's just
Yeah,
a dark
the
area.
lights are missing on those boards for some reason. Like, I don't know what happened. I'm sorry about that.
Yeah, a lot of spooky stuff has happened. Um, yeah, I'll just open them up. It's okay. Um, yeah, so it creates those instances from some underlying data, and when that underlying data changes, it computes whatever the difference is and applies those differences. Um, but the issue is that it's very much like, because the use case for Roact is for creating quite dynamic UI, um, which usually isn't on the order of tens of thousands of instances. It's like low hundreds usually. Um, there's no real concerns about. It's not made to handle any like super high demand performance constraints or memory constraints. And on both counts, it's kind of like they do care about that, because obviously using too much memory or being super laggy would be bad. But for the use case of making UI, usually uh, it's just good enough essentially. Um, and so what I've created, which is something I call, well, the working name has been render, but I'm probably going to be calling it feather, which is basically named after render is sort of a component of Roact, where like you sort of define render functions, and there's all these other bells and whistles that have essentially stripped away um, to make it as memory efficient as possible in terms of the virtual node tree that it leaves behind. Um, and then after that, I've also tried to make it as performant as possible. Um, so the main challenge of doing all this was actually, I sort of know, you can know how Roact works. Sorry, you can know how to use Roact, but that's very different to like knowing what it does under the hood. And so I after like going through this process, I've like understood that a lot better. So I'm going to like explain to you now how that works. So the main ingredient, oops, I should make my pen smaller. The main ingredients are elements, and for me, I'm just using two kinds of elements. So the first are host elements, and these consist of two things. Well, really, every element consists of two things, but it can change depending on the type of the data involved. Changes depending on what kind of element it is. So uh, every element has a component, which in this case is a string, and it also has a table of props. So I'm just going to type it with the word props with a capital P. But just to explain what that is, let me gather a collection of types up here that I'll use. When I write props, that's just shorthand for it's just a table, like any table, just mapping keys to values. And so in the case of when you have a host element, this props table maps instance. It sort of tells you what happened there. Something crazy happened. Yeah, I don't know what that was. It sort of defines the instance properties. And I should say that this component here is it's a class name. So it could be a pod or something, or a frame. And so then these this table props the keys have to be valid instance property names, and then the values have to be they're just the values of those properties you want to assign. There is also a sort of special prop as well, which is props, and then there's a special key that the render module allows you to access, but it's just some way of distinguishing the table of children, and that maps that is a map from keys, so like however you want to index them, to elements. So because I've only written host elements, like at the moment, the only example you have of another element here is another host element. So if you have this is just the child relationship of like child-parent relationship between instances. So clearly, the host elements are descriptions of instances, and they can, using the children key in the props table, you can describe instances that are parents of other instances, and so that describes that relationship. The second kind of component, which makes this interesting, I don't know what the heck is happening here with the writing. The second kind is function elements. And here
my theory is today the disruption boards were completely well behaved, so I think the possessing spirit has moved to this board.
Must be. So here the component instead is a function from props to some element, and the props are just some prop table. So you can think of this as like it's a decomposed function application. So it's like you've got the function that can apply props to that can take in props and output an element, and you've also got the props, but you've kept them separated for some reason, and we'll see why. Okay, so this is on the description side of Roact and render. This is how you describe what you want to see using host elements and function elements. And now I'm going to explain what we actually do with this. Is we create a tree of virtual nodes. And this creation process was kind of somewhat mysterious to me, but I've got a better grasp on it now. So, firstly, the story with host elements is pretty straightforward. So, given some host element, you can turn it into a virtual node as follows. Firstly, you have the host instance. And this is just some instance, and clearly this is going to be equal to instance dot new, and then you take the element and you call dot component. So yeah, you just create the instance based on the class name that's provided in the element, and then you also store. Well, in Roact you store the props. I don't actually store the props, but put them here. And you remember what the component is, because it's faster to. I'm pretty sure it's faster to store this and check whether the component has changed here rather than looking up the dot class name of the host instance. I'm not super certain about that, but I think that's the case. And then there is the children. And so this is before, like, if you call props, if you look up this key in the props table, you end up with a function from keys to. Sorry, you end up with a table from keys to elements, but I'm describing a translation from host elements or from elements to virtual nodes. And so clearly, once you translate these, once you apply this mapping once, you can then recursively apply it to all the children in the props table because they're all elements. And then you'll end up with a map from keys to virtual nodes. So that is the anatomy of a host virtual node. Function elements, what virtual node do they get turned into? It's pretty simple. It's a result, which is you just apply the component to the props, obviously, as I was saying before. And that gives you an element, but again, you can just recursively apply this this mapping from elements to virtual nodes, and you'll end up with a virtual node. Which may itself be something that arises from another function element, or maybe it's from another host element, and you'll get a host virtual node. You also store the props and the component. And so I want to now sort of give a sort of visual explanation of this mapping. So say on the element side, you start with some host. Maybe that's a folder or a model or something. It describes say a folder or a model with some properties or whatever. Just the top instance itself. So it could have children, which maybe you have. Maybe in this table here, this props children table, the first thing is like a function element, and then maybe you have another host element here, and it could have children of its own, which is maybe another host element, and maybe there's another function element here. So these downward arrows, they are denoting some. This is a key value relationship in this children table. Now, if once we apply this mapping, what we end up with is we end up with, at the top, the host element becomes a host virtual node. So I'll just write instance because it has an instance in it. Sorry, let me write that better. And now what are the... So this is a host virtual node. It has all of this stuff in it. So it has the host instance, the props, the component, and the children. And so let's draw the children. The children will be, well, firstly over here, you end up just with another host virtual node. But on the left here, you get a function virtual node. So I'll draw that a bit differently. And I guess actually on this side, I sort of want you to think of these relationships as like actual child relationships. And then what happens with these function virtual nodes is it's sort of like an in-between like guard between between a host instance and its actual child. It's sort of an intermediate thing. So maybe this function component, it actually it results in the result it stores is another virtual node, and say that could be another host instance with like 2 children, which themselves will become host virtual nodes. So maybe I should have written I there. But yeah, so you can see that there's 2 kinds of things that happen in this mapping. The host elements become host virtual nodes and have actual instances inside them, and the function elements sort of, they like the stuff below them doesn't exist yet, but once you evaluate the functions and recursively like create the virtual nodes or the elements and then eventually the virtual nodes below them, you end up with eventually just a bunch of host instances with these function virtual nodes between them. Now let me draw the rest of this tree. Maybe there's some more host instances down here. Does that make sense? Okay, so the problem with this is, and what I've identified and solved with Feather is, the problem is the host virtual nodes, they store these props, and usually these properties are the actual the properties that you assign to like that you set on the instances, and typically there is a lot of redundancy in them, in that they are derived from simpler data. So for example, every single part on part on this board, sorry, it's a bit dark, is anchored, and therefore this props table will sort of store anchored equals true for every single host virtual node. And yeah, also like you'll also have, say, like the defining data of a line on this board is really just 2 points, like it's just two vector 2 values. But that gets sort of translated into, in the case of the parts, it gets translated into a C frame, which is like what, 9 or 12 numbers, and also a vector 3 for the vector 3 for the size. So the going from the underlying data to the host elements, and then the host virtual nodes, you end up sort of the amount of data sort of multiplies, and the source data is usually a lot simpler. So my solution is essentially, well, first off, you need to just get rid of the props table, and I just sort of began getting rid of as much as possible on this side of on the virtual node side. I've sort of considered. I actually also get rid of the component, because the use case that I'm in, usually the overall structure of the tree and the kinds of instances that you see at each level doesn't sort of super dynamically change, and so that, like, you don't need to say you don't need to account for the case where like a part actually turns into a wedge part or something. So all of this amounts to like a lot of sort of redundant data that I don't actually make use of. And I guess maybe I can highlight the problem now, that I solved. So let me just change windows. To here. Okay, tell me if I'm cutting out at all. So this is using, you might be able to see here, I've written test for super unoptimized. This isn't exactly the original version of using Roact for metaboard, but it's I sort of backtracked to what I was doing before to redo this test. So I'll show you what this test does. There's a lot of this code here isn't very clean, but essentially it just makes a bunch of random curves, which are just sequences of points with some width and color data and the z-index. And then I used this Roact component, which this is an example of a function component. This part canvas thing is kind of a function, and it takes in these props, and it will create a tree that will result in drawing all these figures. You can see here I've set the memory category in the debug module so that I've labeled this as test 4 because I was doing a bunch of tests. I also include the word physics parts. That'll be clear in a second why I did that. So if we run this, how it works is when I press the middle mouse button, it will create the instances. So first I'll bring up the so when I search physics parts in the memory profiler, I did that because I wanted to see the physics parts. This is actually, the memory usage of all the parts in the world. but there's a massive memory leak in Roblox Studio like all the time, where this will just sort of go up as you use Roblox Studio, which is stupid. But you can see this is the memory usage of that script, or the thread associated to that script. Right now it's at 0.002 megabytes. And so if I hit, let me just get rid of this. If I hit the middle mouse button, just creates a bunch of lines here, draws all that. You can see physics parts has gone up by about 46-ish. Or is that 56? Yeah, roughly 56 megabytes. And this is that virtual node tree, but with Roact, it's gone up like 42.6 megabytes, which is so almost the same amount of data as the parts themselves, which is huge. And so I went through a couple iterations with this where I tried to get this as small as possible, still using Roact. I think this one was a little better. Essentially, I did things like getting rid of the I can show it. Where is it? Here? No, it's not that. Test 4, is it? Yeah. Yeah. That was just one of my random print messages. Here is I forked Roact and added this like ability to set custom default properties for the hosts. So like I make sure that every single part already has anchored equals true. And this partly solves this. This brings it down to roughly about 18 megabytes. Once I do some other optimizations as well. But there's still a lot more redundancy. So let me show you the actual module now. Make this a bit bigger. Okay, so this is it's really simple. There's just the create element function, which just stores the component and the props in a table, and there's this update virtual node function. I guess we could go through how it actually does things. Okay, so so we need to. So this sort of does both the job of creating the virtual nodes, but also updating them. So if you pass in an empty piece of data, so if there's no virtual node at all, it will seek to create it. So if there's no host instance, then if there's no host instance, then we create it. Okay, I didn't explain this. We set the initial properties for it, and then we store it there. And then we go through and okay, there's a lot of details here that I haven't sort of got to. I think instead I should move into I'll talk about the delta children thing. So usually, here's an example of, here's a simple example called board 2D of making components here. So firstly, this is, this takes in a table of curves, which have some ID and some curve data. And in this sine story, like you might be graphing some function, and see here I'm graphing 3 curves and passing it into the board 2D component. And this is just the function that creates the points out of some parameters for the sine function. So you pass it into this component, and what does the component return? It takes each curve and calls this. There's another part curve component here. So the this component, this board 2D component, returns a host component which has a table of children, which are each of the curves, and each of those are one of these part curve things, and they themselves, the curves are made up of lines, and this is another component for creating the lines. And so you can see here, this is where this is an example of the underlying data, which is just a bunch of points. See here that this is just an array of vector 2s, and there is a color, width, and z-index, which is associated to the whole curve. And so what I avoid with, I guess one of my main things that I do with this module is I'm avoiding all of this data, the color, width, and z-index especially, from also being from being stored with every single line component. So I do sort of make use of them, but the fact that host virtual nodes don't actually store any of these properties means that the memory usage is cut down a lot. And in the end, I've managed to get the memory usage. So before it was 44 megabytes down to 18 megabytes. I've now got it down to about 2.9 megabytes for that same exact test. And like it's all well and good to just like throw away the to just throw away the data from the virtual node tree. The question is, you just need to make sure that you can make updates when you need to make updates, and that like by forgetting all that data, you haven't prevented yourself from knowing what things need to be updated. And so with this module, the point is that I make the host components or the host virtual nodes just forget all this data. And if you need to remember data, you do it on the with the function components. So by default, the function components are pure components in the sense that if any of the props change, then that section of the virtual node tree will be re-rendered. But if none of them change, then none of it is re-rendered. Is there any questions yet? Anything I can clarify? Anything you want to see? Okay. I just want to motivate this whole Delta children thing. So given just this, it's not actually possible to, like, if the story ended here, every time you call the update function, say one of the points changed that that gets sent in this points table in this prop here. Say the points table changed, so because one of the points has moved, and therefore this gets re-rendered. We call the part curve function. It returns us this big component that has all of the lines as the children. We're still stuck with the same scenario where we have to call this curve line component function, or we have to regenerate all of these host elements, and then we can't actually compare their data because we've thrown it away. And so by default, what render actually does is, you can see here, no matter what, it will update all of the props, which is kind of counterintuitive, because the point is to only update where you absolutely need to make updates. You don't want to just update all the properties of every single line just because one of them changed. So it's kind of like, how did I actually, like, if, since I'm not storing the props in the virtual node, I have no ability to actually make this comparison between the new element that's come in from this component, which is all of these host components here. I have the props for these new host components, but I don't have the old ones. And so the way that I get around this is the Delta children version of this, which is instead of storing the props in memory for, like, the old version of the component, is putting it on the module to, like, figure out what the differences are and what it needs to change. But the whole point is that we know that this underlying data, that this array of points, as well as the color and width and z-index, we can all, like, we can take that data and figure out exactly which children need to be changed. And so the way that I do that is, this is the second version of this part curve component. I extend the definition of a function component so that you're allowed to take in the old props, because we do store the props for function components, like in the function virtual nodes. We just don't store them in the host virtual nodes. So my thesis at the start was that the data is the smallest, like, uses the smallest amount of memory, like, the further up it is. Like, as you go through the tree, it gets sort of translated into, like, more and more redundant data. So the function components, the old props and the new props, get stored in the virtual node. So this module allows you to take the old props as well and use that to specify, instead of the children, I've got this concept of delta children, which is just the children that need to be changed and updated in some way. And so that's exactly what I'm doing here. I guess I'm just accounting for the fact that maybe this is the first time this is being rendered. So if there's no old props, then we want to render every single one of these children. But okay, if the color has changed, then we want to render all of them. But if the ith point or the I plus 1th point has changed between the new prop points and the old points, then we know that particular line, because it depends on those two values, needs to be updated. So we insert it there. And so this is my version of we're taking back control from the from render, like from the our version of Roact, where instead of just giving it the resulting like host components and saying, please remember as you go so you can figure out what's the difference between all the props between the new and old host virtual nodes. Instead, we know we can derive the difference like in a much faster way, because it's much faster to do these checks here than to generate all the children and then check all the props for all the children. So that's what delta children is for. And you can see, so here, like, so you get back more control, but ultimately this means that you have more responsibility to so with great power comes great responsibility. You're responsible for like being correct about which things need to update. So there's also this concept of I made a special subtract child key, because the things that you don't insert, like the key value thing will be like if you insert the value nil for a particular key, it's no different than if it just wasn't there at all in the table, because that's how Lua works. So and semantically we have two different things that we want to express in this table. That we want to say that anything that's not in this table we don't want to change, because we know that it's completely unchanged. But we also might want to remove elements from this table, is the point I'm trying to make. And so in those cases we might return subtract child, which I haven't actually done anywhere here, because this is a sort of simplified example. But coming back to this, so if the new element that we're updating with has a delta children table, then you go through that table. If the value is a subtract child key, then you destroy that virtual node and set its value to nil. Otherwise, you cause an update, and that will pass through to this component actually being called for all those child elements. And so ultimately, because I'm not storing the props, like even if the color hasn't changed, I'll still set it again. But the idea is we can make this part of it as small as possible. You could also, like, because you have full freedom in what you return in the delta children table, you can also like return less props here, even like if you know that the color hasn't changed, you can sort of set, you can this is just a regular function here I'm using. You could also parameterize this so that you like maybe don't return the color, but specifically for this use case I've made it so that like if you've just got some like initial stuff that you need to set, and then you know that you're not going to change it in any update, I made a special key for that, which is host init props. And so that sets the that's what's happening here, where uh, when you first create the instance, it looks in that table and sets all those values. And then once that's been created, these values never get looked at. So you only ever apply uh, the regular props every time you re-render a host. So the name of the game is to call it, the name of the game is to re-render the host as little as possible, and when you do update those hosts, you want to update the smallest number of properties as possible. It's not the end of the world if we had to reassign all these properties, because Roblox actually does a check in the back end already, so that if the new value is the same as the old value, that like if you try and set the same value on an instance that it already is, then it checks for that and then doesn't fire any changed events. It doesn't have any more broad effect. But I think it still is slower than if you don't call it at all. Even looking up the class name or checking what the parent is, I think incurs some cost that is sort of not significant when you have a smaller number of instances, but when with metaboard, we're working with tens of thousands of instances. It certainly adds up. So that reminds me of another comment I wanted to make, which is this. The thinking behind this module was going a lot towards the metaboard use case, in which largely almost nothing about the board of curves changes, except for one part of one of the curves. It largely stays the same. And you can see this when I'm talking about these delta children. This delta children idea is that this very much takes advantage of that. So that it's very fast to actually perform an update. But this is kind of useless in the case of sorry, it's taken a while to get to the pretty pictures, but in the case of graphing cool looking functions in 3D, which is some silly example. You can see every single instance is changing every single frame. So I can't really claim that this is sort of the best, most performant way to create things like this. Though the sort of framework of writing function components which translate underlying data into host instances with all the props set derived from that data. That framework is kind of nice to use. And I guess the more you have things appearing and disappearing, and the properties changing in sort of complicated ways, the more I guess it's quite useful to use render instead of manually maintaining the instances yourself. So there is some overhead with render in terms of creating all the element tables that it does along the way. But so often the actual C framing or the instances themselves is usually the bottleneck. I should pause for questions again, but I have some more I want to say.
No real questions. So I guess the advantage of using render over Roact for this particular demo is still there because of the memory usage, right?
Yeah. So it. Yeah. So it's if you're just making one of these, then like I guess the memory usage doesn't really have much of an impact. But yeah, it really adds up like in the sort of metaboard case. I found, I think if you're doing something where all the parts are moving all the time, like this, you will hit performance problems before you hit memory usage problems if all of them are always moving. I've tried to alleviate it as much as possible, which uh, I did something pretty interesting, which I think is kind of nice. It's this bulk C-frame thing. So you can, so here in board 2D, or maybe it's board 3D. Yeah, I use dot, instead of just setting like the C-frame key to a C-frame, I made a special key called bulk C-frame. And what I actually do is instead of individually setting every C-frame for all the instances that have this, what you can do is you can add it to an array of parts and then the C-frames for those parts. And then when you call the update function for render, it does the update, then checks if, yeah, and then it uses this workspace bulk move to function, which according to the dev forum is faster once you pass about 50 parts. But I've sort of like it definitely improves it. But once I get into like a lot of parts, I have trouble with like the sort of frame rate starts getting affected. Also, it doesn't really help if you're doing it on the server, like the replication sort of doesn't. I don't know if it like if it's not using bulk move to on the replication or what, or but yeah, it's not very good watching it over the server, which is kind of a problem. Here's the other example where
Yeah.
I called it Pringle. I don't know. Is there like a name for is it saddle or something?
That's just the saddle, yeah.
Um,
It's much easier to see animated, actually. People had trouble during the class actually interpreting where the various features were. So now it's
yeah. So I can show something cool we can do with this is instead of, so right now I'm connecting to Heartbeat and just calling render update, graphing the whole thing again with depending on the time. But instead of that, whoops, you could make a control part. Why isn't target defined? Target is just workspace. And then when that controller part moves, we can update the graph. We don't need start time. Let's see if this works. Is it making a part? I think it's making it, but it's invisible. Oh. I've done two different things here, which is weird. Yeah, this is what I want. no adorny part. Wait. I think I need to fix something about board 3D. No, maybe not. What's this? Is that it? I don't think it's C-framing any of the parts. I think it's just putting them all in the one spot. It's not doing what I claimed it was doing. Every single part is right there for some reason. Board 3D. Bulk C-frame. Oh, right. This is an old one. Go. Just need to actually read my code. When I did it with Heartbeat, it was fine. So it's not anything in render, it's something here. Oh, sorry. Yeah, I still just haven't even read my code. This one is more correct than the other one. It's because I was using an old API for render, which is update virtual node. Control part. Okay. Value. Okay. Sorry, I'm conflating two different things. It's not moving. Oh wait, is it? Is it because I'm moving in like integer units or something? Yeah. Okay, it did work. Okay, so yeah, I'm just sort of imagining some kind of use case where, uh, like I don't know, like maybe tweak something else about it, but like if you could like interact with this in Roblox and sort of move it and command the whole thing to move like a wizard, um, that might be pedagogically useful. Um, or even just like cool effects, like if you walk up to it, it sort of like reacts to your where your position is or something.
Well,
Um,
yeah, you would. The most obvious use case is to vary the actual surface. I don't know if you have the formula there, but I could give you a different function to graph where you would see.
oh yeah, let's do it. So I'll show you what I've got here. It's uh, so phi is a function of what is this? There's u and v. Okay, yeah. So there's a function of u and v, and I'm tweaking v a little bit by this phase value, which is the one that I'm passing. Oh no, is that what I'm doing?
Where is it in the formula? I don't see it. Oh, it's I equals minus 1 n plus v phase. Okay, you're shifting the domain. So you're shifting the domain that you're graphing on, if I read that correctly.
I thought I was going to pass in like the t value here or something. What is so t becomes p by doing mod 1, so I just get the decimal part, and then for I from n. Okay, this is where it's the u value. Actually, this is the one that I'm slightly tweaking, and this one I just haven't tweaked at all. So u is getting slightly tweaked left and right by this p value, which is from the
so
time value.
You've got v times u squared minus v squared, and then u squared minus v squared.
So remember, these are swapped because I wanted to orient it differently, because the y and z axis are different in mathematics and Roblox.
Yeah. Okay. Yeah, let's think. So try putting. Wait. So what's getting tweaked? It's getting tweaked before it even gets into this function, right?
The u value is changing, but we could set this up to do something else. That this u value is slightly is being shifted.
Yeah. Okay. Then that's.
But I mean, I could just introduce another parameter, s, and then vary that however you like if you wanted to.
That would be better. Yeah, let's do that.
So what, like?
Well, I was thinking. So this the saddle. So you're graphing. I mean, it's a little weird. I don't. Why is there a u squared minus v squared in the second coordinate there? So the height above the UV plane is the first number, but no, it should be the second number. So I don't really understand what this first number, v times u squared minus v squared, is doing. Oh, it's the color. No, it's not the color.
No, that's the x coordinate.
It's the x coordinate. Why is the x coordinate not just v or u?
Like the z coordinate is u.
Okay, so one of them should be u, one of the other coordinates should be v, and then the third coordinate, which is the height above the plane, should be u squared minus v squared.
Yeah, that's this.
Yeah, so I don't know what this first coordinate is doing. What does this even mean?
I took this from the mag lecture.
Yeah, I know. So I'm asking what the hell I was doing. I must have must have wanted to squish it somehow because it didn't really fit into my volume, and so I did this kind of crazy thing. Just try changing that to V. I think I must have had V originally, and then I decided to scale it. Yeah, that's a number between 0 and 1, so I must have decided to scale it. But if you just change that to a V, it probably looks similar. Yeah, but it doesn't fit in the thing. Okay. I don't know what the orientation is. Try V times 0.1 or something. Okay.
Wait, I don't trust this. Okay, yeah, it's this thing. Let me get rid of the controller thing. And go back to this. I think it doesn't like when I plug in 0. Heartbeat. We got the control part. Okay, so if I go back to here, I can change this to V should just be fine. Cool. There's the saddle.
Okay, that looks neat. Okay, so now try graphing instead u squared minus v squared plus your parameter times u.
U squared minus. Wait, what's the s times u? Is that it?
Yep.
Is that what you mean?
Mm-hmm.
So s, I'm not passing in anything, but I could pass in p goes from 0 to 1.
P is the control parameter. Whoa. Yeah, okay.
So that varies it with time.
Mm-hmm.
We can do something else. We can also type in math.sine. Oh wait, I thought it would go back and forth. Wait, 0. Oh.
Minus 1. Rockabye, baby. That's cool. It's very jaunty. Okay.
Let's vary the size.
Turn Can Collide on and stick it in TRS, and we're done. Whoa. Okay, there you go. That's pretty cool.
I'll change it back to sweet.
Whoa. All right. Doof, 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 doof.
Yeah, it's moving pretty well with the this is running in studio. It runs a bit faster when you actually play it, not in edit mode.
Right.
I'd say if we increase the number of circles to 30,
Yeah, I see.
I'm basically already on the threshold of moving all of the parts at once. Moving this many parts, it just sort of starts peaking. The other thing is that I actually I can demo this just by changing. I started playing around with handle adornments again. Okay, this is already broken. Um, yeah, okay, I can't demo the handler dormants, but I also just did a bunch more testing with them, and what I found is I think it's sort of it's kind of subtle, the difference in performance. So I think handler dormants. So firstly, in terms of memory usage, they use about a quarter of the memory usage, um, but their frame rate, the just in terms of performance, it's kind of like constant with it's just a linear function of the number of handle DOMs you use, and it's not really affected by where you're standing. Whereas, like with parts, it sort of depends where you're standing and where you're looking at the parts and how they're like intersecting each other. Where like you can see the performance go up and down, like, and it usually settles to being fine, but when you then look at it from a new angle, it might go bad again. Um, and yeah, so it's kind of like when you're below the like a threshold where I think at like 40,000 instances, I think the handle adornments were still doing kind of better than the parts in that they were sort of constantly like still pretty good, but the parts were like varying between still pretty good and like really bad, like depending on how you looked at them. But then sort of when you go above 40,000, uh, like like they're both kind of bad, but like the parts stop being bad when you're far enough away of like from all the parts. So I think that means that like I was sort of briefly wondering if we can sort of take advantage of handle adornments again, but I think that fact that they like the performance doesn't increase again when you walk away from them, um, yeah, is so for the metaboard use case. I think that means you can't. They're not really useful, but I think there's many cases in which if you're just graphing something and it's like moving all the time, it might be a better idea to consider handle adornments for those cases. Um, doesn't look as pretty though in that like you don't get any of the like the shine on them at all. Like they're kind of just a blank circle. Um, I don't think. I had a twisted cubic example, and I think it's broken though.
Oh, I saw that in the video. Yeah, that was pretty cool.
All right, I should probably leave it at that.
Yeah. Thanks a lot, Billy.
Thanks.